So now I want to talk about one last thing, which is learning with missing values. So we've dealt with this non-formatted categorical data, and now we need to deal with the fact that some of our values are missing. And so why doesn't the bloody machine learning toolkit work on this? There is a fundamental reason, is that machine learning models in general tend to need entries in a vector space, or at least a metric space, or at least an ordered space. It's just easier for machine learning to draw analogies if it knows links between data, and missing value is nowhere there. So it's slightly more than an implementation problem. There's a fundamental problem there. There's a very, very advanced and thorough literature on missing values in statistics. And let me summarize it really quickly for you. The canonical model is that we have a generating process for the complete data, and B, a random process that occludes the entries. This is really the conceptual model on which the classic results stand upon. And then there's a really classic situation which is known as missing at random, MAR, that says, hand-waving, that for non-observed values, the probability of missingness does not depend on the non-observed value. This might seem a bit mind-blowing. If you look at the actual definition, it's even more mind-blowing, and people simplify it because it doesn't really make sense. And it's true, it doesn't really make sense. The reason there is this definition is that it allows in a likelihood framework to prove that, and that was proven by Rubin 40 years ago, that maximizing the likelihood of the observed data while ignoring, marginalizing in technical term, the unobserved value will give the maximum likelihood of model A, of the model of the complete data generative process. Okay? So it means that if you are modeling your data, if you're doing classic statistics, you're modeling your data with likelihood models that you believe, and you believe you have an occluding process, you can still solve the problem when you're in a missing at random situation. Conversely, if you're, and missing completely at random is a special case of this situation where the missingness is independent from the data, and it's it's a special case of missing at random, and it's easier to understand. And the theorem still applies. Now, conversely, if you're in a missing not at random, if you're not in this situation, then missingness is not ignorable. If you try to maximize the likelihood while ignoring the missing data, you will have problems. In practice, what does it look like? I've shown you a complete data. I've shown you a missing completely at random. So basically, I've subsampled. So here, I'm deleting my missing values. They're not on the data set. So I've subsampled. That's a problem. And I'm showing you missing not at random. And what you're seeing here is that we have some form of censoring process. And part of the data distribution is not well represented. OK? So this will give problem. Now, I would like to say that this classic statistical point of view is not of interest to us here, or at least not completely of interest. And we shouldn't take those results as fundamental results for machine learning. There are two reasons. One is there is not always a non-observed value. For instance, what is the age of the spouse of people who are single? So even this assumption is broken in many, many, many data sets. And the second one is that we're not trying to maximize likelihoods. We're trying to predict. Now, based on this, we can just do machine learning. But the bloody machine learning toolkit still doesn't work. I've given you theory, not practice. OK, practice. I'll come back to this theory later. Practice. We can impute. And this goes back to the theory before. Imputing means we're going to fill in the information. We're going to guess things for those values we haven't seen. And once again, there's a large statistical literature, but it's focused on in-sample testing. Doesn't tell you how to complete the test set, and doesn't tell you what to do with the prediction. So let me cover a bit the tools we have in scikit-learn. There's mean imputation, which is a special case of univariate imputation. And we can, for instance, replace the missing values with the mean of the feature. So this is done with the simple imputer. There's conditional imputation, the idea being that you're modeling one feature as a function of the other, and then you can learn predictive models across features, and then you can predict missing values, okay? There are classic implementations in R, and we now have an implementation in scikit-learn that can do this with linear models or random forests or other things. The classic point of view tells you that mean imputation is a very, very, very bad thing because it will distort the distribution. So as you can see here, I've imputed the missing data with the mean, and you can see that we're collapsing the variance of the data along one direction. So we shouldn't be doing that. Classic point of view. And there are conditions that are known as congeniality conditions on an imputation that tell you that a good imputation must preserve the data properties used by the later analysis step. Now, we've looked at supervised learning in this setting, and we've shown we've proven that if the learner is powerful enough, like a random forest or a gradient boosted tree, imputing both the test and the train with the mean of the train is consistent in the sense that it converges to the best possible prediction. And the reason is, A, we're not trying to maximize likelihoods. B, the learner will learn to recognize the imputed entries and will compensate for them. So the learner basically learns those biases in the distribution and fixes them. So we don't have to worry about the classical results. In practice, you can see it here. I'm comparing mean imputation and iterative imputation, and what we can see is that if I have enough data, they perform as well. If I don't have enough data, then the iterative imputer does better. The notebooks are online, and the slides are online. So the conclusion is when we have enough data, iterative imputer is not necessary, mean imputation is enough, but when we don't have enough data, iterative imputer helps. Now, it may not be enough. Imputation may not be enough, and here's a pathological example. Why? What I'm trying to predict depends only on whether the data is missing or not. Suppose I'm trying to predict fraud, and the only signal about fraud is that people have not filled in some information. So this will fall into missing not at random situations, and in such a situation, imputing makes the prediction impossible. Okay? So if I impute, I'm losing this information, and I can't predict anymore. So what's the solution? The solution is to add a missingness indicator, an extra column that tells me whether or not the data was present, so I can impute, but also expose to the learner whether or not the data was present. And if I do this, so this is another simulation where we have specific censoring in the data, and if I do this, what you can see is that both the mean and the iterative imputer are consistent. They converge to the best prediction if there is the indicator, but the iterative imputer doesn't work well at all if there is not the indicator. And also what we can see is that here, so adding this indicator, this mask is absolutely crucial. And the other thing that we can see is that iterative imputation in this situation is actually detrimental because it's making it harder for the learner to see this missingness pattern. All right? So basically we have two situations, one where the missingness is not informative, in which case the iterative imputer is better, one where missingness is informative, in which case actually iterative imputer can harm because it makes it harder for the learner to learn this informative missingness. Okay? Now to wrap up, learning on dirty data, first take-home message, prepare the data via column transformer. That's easy. Second take-home message, use gradient boosting. In my experience, it really works well on this kind of data. It's robust to all kind of word entries in the data. First thing you should try, probably. Dirty categories. So we're interested in statistical modeling on non-curated categorical data. Please help us and give us your dirty data with a prediction task. It helps us benchmark what we do. It's very important. And we have similarity encoding and more work that's coming up really soon. Supervised learning with missing data, mean imputation with a missing indicator is actually a pretty good choice. There are many more results in the paper. And in general, if you're interested in this area of research, we have this research project that we call Dirty Data, where there is ongoing research and there will be more. Thank you.